to lecture 19 of Dynamical Systems. Today we're going to go on and try and fix what we had wrong with the regular perturbation theory in the last lecture. So if you remember, we did the regular perturbation theory and we found that just assuming that the answer was a series expansion in epsilon was not enough. It only captured the dynamics for the beginning part of the evolution. As time went on, the answer departed quite dramatically. And I said we hadn't captured the small slow drift in period and the slow drift in amplitude. So we're going to now give a prescription that is going to fix that. And I want somebody to hit the lights, these ones that are shining on the overhead projector, please. Okay, so the method that fixes, the method that fixes the regular perturbation theory is called two-timing. And what you do is you basically assume you have two time scales and you treat them independently. So what you have is you say you have two time scales, they're independent. You have a fast time scale that basically goes with the oscillation of the oscillator, and you're going to call that order 1. And then you're going to have a slow time scale, and you're going to have a variable associated with this fast time scale that is in fact just tau equals to t. And then you're going to have a slow time scale, and it's going to go like order epsilon, and you introduced a new variable for a big T that goes like epsilon times t, okay? And you must view tau and big T as two separate things when you do the calculation, and that's very important, okay? So you view them as independent, and then when you do this calculation, you basically expand your solution that you're going to put back into that weakly nonlinear oscillator equation. You're going to assume your solution is now a function of time and epsilon, so that's general, and it's going to consist of a base solution that has a slow time scale, that big T, and a fast time scale, and it's going to have a second solution. The next order is going to have epsilon times your second solution, which is also a function of a slow time scale and the fast time scale. Okay, so now if you remember the original regular perturbation theory, you didn't have this idea of a slow time scale, so that's what's new. And what's also new is you're considering tau and big T to effectively be two separate functions, even though or separate deep independent variables, even though you know that they are in fact connected. Okay. And so the way we go about finding the solution is to substitute this assumption into our weakly nonlinear equation and then do certain calculations to try and actually solve it. Okay, so the methods we're going to use are very, very similar to what we did with the regular perturbation theory. We're simply going to substitute our assumption, the blue thing, into the red one, and what we get then is we're going to get expressions for what x1 and x2 are, but we're going to get their dependence on tau as well as on t. And to do that, the first thing we're going to need are these derivatives, right? We're going to need what x dot is, and what x double dot is. Okay, and that's where all the meat of the calculation goes in, and it's important to do it correctly. Okay, so we're going to use the chain rule to evaluate that, and so any function we're going to simply define its time derivative as df dt, but the thing now is when we start finding out if the function is a function of both t and tau, then its total time derivative is just the chain rule. It's df d tau multiplied by d tau dt plus df d big T multiplied by d big T dt. Okay, so that's what I mean by we treat our two slow and fast time as independent variables. And we can now go, and now we can use what we know about the slow and the fast time. We know that d tau dt is just 1, and we know that d big T dt is epsilon. Okay, so we now have a rule for the total time derivative. It's simply df dt tau plus epsilon df d big T, so the time derivative with respect to the slow time. And f double dot, we're just going to apply this thing twice. So we're going to say it's ddt of f dot. So ddt is again equals to just dd tau of f dot plus epsilon times dd big T of f dot. But we already know what f dot is. It's this thing. So we're going to now substitute this thing into this expression and expand it. Okay, so we have dd tau of this df d tau, so we get a second derivative, plus epsilon times dd big T of f dot. Okay, so it's epsilon times dd, oh no, wait, I'm too fast. Okay, so sorry, I'm still doing this first one. I'm still dd tau of f dot. So I have the second derivative with respect to tau when we do dd tau here, and then I take dd tau of this thing as well, and then I get that thing. So there I have epsilon times the second derivative of f times dd tau times the big T. Okay, and now we're going to do the second term, and then we're going to get another one because it's epsilon times dd big T of f dot. So the first term is dd big T of this thing. So we have epsilon from there, and then we have df, the second derivative of f with respect to the slow time, and then the fast time. And then if we look at the next term, we're going to have epsilon times the second derivative with respect to the slow time. But because we have epsilon squared, we can just ignore it and we can say it's ordered epsilon squared. Okay, so the full second derivative of f is basically this thing. Right, so we basically have this first term as the second derivative with respect to the slow time, and 2 times epsilon, the derivative with respect to the second derivative with respect to the fast time, and this is the derivative with respect to the fast time and the derivative with respect to the slow time, the partial derivative. So you can see the tricky part of this whole expression is writing these time derivatives out, taking into account that you have a fast and a slow time. And so I strongly encourage you to actually do this at least once so that you can do it on your own. Okay, so we're now going to put these assumptions or these definitions for derivatives into our ansatz that we have for x, and we're going to use that to actually evaluate this thing. Okay, so we're now going to have x dot is equals to, remember x is also an expansion, right? So it's basically x0 dot plus epsilon x1 dot. Okay, and so x0 dot is just ddx0 d fast time plus epsilon ddx0 d slow time. Okay, so I'm getting it from up there. And what we have also is that the x1 dot is epsilon, so there's the epsilon times ddx1 d fast time plus epsilon times ddx1 d slow time, but here you have an epsilon squared, so you typically can just ignore that term. Okay, and so we take the next step and just simplify it. We have dx0 d tau plus epsilon times dx0 d slow time plus dx1 d fast time. Okay, so you can see how the different orders are combining in a slightly less trivial way than what they did with the regular perturbation. And the second derivative we can also work out, it's just the second derivative of x0 plus epsilon times the second derivative of x1, and except now we're going to use this expression over here. So what we're going to get there is this expression for x0, so there it is, the second derivative with respect to the fast time, plus 2 epsilon times x0 with respect to the slow time, and then with respect to the fast time, plus, and then we just keep the first term, epsilon times the second derivative of x1 with respect to the fast time. Okay, so the orders are combining in a slightly non-trivial way. What typically happens is you have a derivative of a fast time for the next order up combining with the derivative of the slow time for the previous order. So this happens here for the second derivative. It's also happening over here for the first derivative. Okay, so let's do it in our example. Remember, we had that nice example that we had the exact analytic answer for, and we used it to show that our regular perturbation theory was only getting the right answer for a reasonably short amount of time. Let's use this method now on the damped oscillator. So there we have a very simple H effectively. Okay, the initial conditions at times t equals to 0 is simply x equals to 0, and the derivative of x at 0 is equals to 1. And we're going to substitute the expressions for x dot and x double dot into this equation. And what we do then is we get the following thing. So this is x double dot that I just got from over here, plus x, which is just this x0 plus epsilon x1, plus 2 times epsilon times this first derivative, which I got over there, okay, and equals to 0. So it's kind of mechanical, which is nice. It's got to be, otherwise you're going to get very confused when you go to high orders. It's an explosive equation, but all perturbation theory expansions are. The trick is just you now go and you collect everything that doesn't have an epsilon in front of it and everything that has an epsilon in front of it. Okay, so it's the same argument, and then both individually have to be 0. So everything that has no epsilon in front of it we call order 1, and we can see it's basically this, the second derivative of x0 with respect to tau plus x0 over here, and then everything else has an epsilon in front of it, equals to 0. So once again, it's our harmonic oscillator solution. With order epsilon, we're going to collect everything with an order epsilon in front of it. So we basically have this first term, so it's the second derivative with respect to fast time of x1, the mixed derivatives with respect to fast and slow time of x0, okay, plus x1 over there, plus this term only, because the next one is epsilon squared. So it's plus 2 times the fast time derivative of x0, and we're going to have that's equals to 0. Okay, so we've now collected the powers of time, and here you can see that this thing looks very much the thing that we had in regular perturbation theory, and it's quite easy to solve. This thing is a little bit more complicated, but once again what it is a sort of a harmonic equation in the fast time for x1 plus this thing that's applied to x0, and you get x0 from solving this first equation. Okay, and once again, before you can solve it, we have to get the boundary conditions. Okay, or maybe you don't. You can just write down, you can write down the general solution for x0, and it's basically x0 equals to a sine of tau plus b sine of tau, except that this is just the fast time. Instead of a and b being constants for the solution, you can have that A depends on the slow time and B depends also on the slow time, because we said nothing of what the slow time does here, but we know it exists. So what we can say is that both A and B are in fact function of the slow time, and we must always bear that in mind when we take derivatives of x0. Okay, so our general solution is basically that you have x0 equals a function of the slow time sine tau plus b a function of the slow time times cos tau. Okay, and now our order epsilon equations basically becomes, I group all the x1 terms which we don't know on the one side, and I group all the terms that are dependent on x0 that we know from above there, or at least we know something about, on the right hand side. Okay, and what then basically happens is these x0s, once again, just as in the regular perturbation theory, becomes forcing terms, in other words, functions of known time for this thing, for the slow term. Okay, so I've just put everything, the essentials that we had up here, and so that I can go on. Okay, so this is just to say the last 3 lines of the last slide. And so what we now want to do is firstly compute what the forcing terms are. So we want to compute dd tau of x0, and that's just a cos of tau minus b sine of tau. But we also want to compute the time derivative, the slow time derivative of that. And to be able to do that, you need to remember that a and b are functions of the slow time. Okay, so you basically have the d big T, d tau of x0, so you have dd big T of a minus times cos tau minus the slow time derivative of b times sine tau. Okay, and just to make my notation easier, I'm going to say a prime is basically the slow time derivative of a function of slow time. So then when I put that back into this expression for the order epsilon, what I'm going to be left with is that, in some sense, the harmonic operator in fast time of x1 is going to be equals to minus the slow time derivative and applied to the fast time derivative of x0. So this is the a prime cos tau minus 2 times the fast time derivative of x0. So there we have just the a coming in. Okay, plus the terms that are in front of b. So the same thing. Okay, so once again, we have a fast time derivative that looks like a harmonic oscillator, and we have 2 forcing terms, in other words, the cos tau and the sine tau, and we're scared of those things, right? Because they cause explosions, right? Remember when we just had a forcing term of the same frequency as the natural frequency in the regular perturbation theory, it caused the solution to diverge, and the same thing is true over here, except that we have the bonus now that we have more freedom. We've told you nothing about A. Okay, and what we're going to do is we're going to use this freedom to actually set the resonant forcing terms to 0. Okay, and so we're going to actually set A prime plus A equals to 0. It's going to be our criterion for fixing A. And we're going to set b prime plus b equals to 0 as well, and that's going to be our criterion for fixing the big B. Okay, so we set the resonant forcing terms to 0 to prevent the secular terms, in other words, terms that have the same frequency as the natural frequency of our oscillator, and so that it basically means we don't have these explosive terms that are occurring. Okay, so we have a prime plus a is equals to 0, and we can immediately solve this. So we basically have a of our slow time is just e to the minus big T times a constant. And similarly, we have the same thing there. So we solve this, and we have that b of the slow time is just b0 times e to the minus t. Okay, and that looks better because remember when we were trying to, using the regular perturbation theory, we observed that the that the actual solution had this decaying envelope. So we are in fact getting back our decaying envelope, which is nice. Okay, so now we're in a position, we've got the general base solution, we've gotten rid of our resonant forcing terms and therefore the divergent terms that could possibly arise. And what we now want to do is get the exact solution, so we want to impose the boundary conditions. And remember, once again, x has been written as this expansion in terms of the slow and fast time. And so if we have that x of 0 is simply x of 0, 0, which is equals to the expansion itself, and it's got to vanish, okay, for all epsilon. So we're going to have that both x0 of 0, 0 and x1 of the slow and fast time are all 0. And we have that 1 equals to x dot at 0, 0. So we go back to the previous slide, we find out what the definition of x dot is, because remember you expand in both the derivatives and the fact that x is in fact an expansion. And you get this expression has got to be equals to 1. Okay? And so then it's got to be true for all epsilon. So what you basically get then is that dd tau of x0 has got to be equals to 1. And this thing inside has got to vanish. Okay. So you've now got all of the initial conditions on x0, which is basically its fast time derivative has to be 1, and its initial value has to be 0. And you have that the fast time derivative of x1 has got to be equals to minus the slow time derivative of x0. Okay, so you can use the conditions on x0 and x0's short time derivative to actually further fix the functions. Okay, so you can use that at times t equals to 0. Remember, a of big T and b of big T are just the constants a0 and b0. And so if x of 0 is 0, then the coefficient of cos has got to be 0, so b0 is equals to 0. And if the second one is if the fast time derivative of x0 is 1 at the origin, it sets a equals to 1. So we now have that our x0 base solution is e to the minus t, the slow time, times sine of tau. Okay, and if I just replace what the slow time is, I get this. Okay, so you can see our base solution is much better than the one we guessed at the previous time. And if we now go on and we compare it to the exact solution, which remember was this thing that we had the slowly decaying part, which was just e to the minus t epsilon t, and then we had this fastly varying timescale part that oscillated, but it didn't oscillate at exactly 1. And we compare it to this function, we can see what our perturbation theory has captured, right? This prescription has basically captured this e to the minus t epsilon, so the slowly decaying part. It's making a difference at order epsilon squared, which is fine because we only expanded it to epsilon. Okay, so we're fine there. And it's also getting the right frequency. Also, the mistake is at epsilon squared. And in fact, if you go on and you plot the two things, you can compare them. Now, let's just write down the exact solution. Remember, I plotted this envelope. So you have the decaying envelope times this amplitude. It looks something like this. And then you have the sine wave in the middle. So that's the exact answer. And I can plot the solution over here, the estimated solution, say for a given epsilon. And what you're going to find is the envelope looks exactly the same for small epsilon, and the oscillation thing is also exactly the same. Right. So, and that's to be expected because this mistake you've made is just order epsilon squared. So up to order epsilon squared, these two things are almost equivalent. Okay, so this way of arguing with the two time scales, and this is the reason why it was introduced, gives us a very good way of having a prescription that we can actually use to get a good approximation of the oscillator. Okay. So now we've looked at one example, and what we would like to do is to find a way of doing this thing for any type of H. Okay, and this is where the averaged equations come in. It sort of takes the development we've made up until this point and it takes it one step further. And just one comment, the notes I've made here are a little bit more general than Strogatz in that I'm now going to start introducing omega squared over here. So it basically allows me to work with oscillators with any frequency. So the reason I did that is because often in physics you're going to get an oscillator value here, and then in order to get it into Strogatz's forms you're going to have to change the time scale to get it. Whereas it's often easier to simply analyze the whole thing with a frequency that's not 1. So this is more general than Strogatz. Watch for it if you have problems that have something that's not 1 coming in there, then you have to use my method and not Strogatz's method. Okay. In fact, what this basically means is you're going to have a frequency in your answers or in those base solutions that actually is omega rather than 1. Okay, so you can do the same game that we did with the two timing. You assume you have two time scales. You write out the derivatives. You put the derivatives into that expression. And then you collect all the terms that don't have epsilon in it for order 1. And what you will get is basically this equation. You'll get two fast time derivatives of x1 plus omega squared, which is now coming in times x0. And if you do collect the terms at order epsilon, you are going to get basically two fast time derivatives of x1 plus omega squared of x1, which is equals to minus 2 the derivative with respect to slow time, the derivative with respect to fast time of x0 minus h. Okay, and remember h is a function of x and x dot. And so you would have to put x and x dot in there, expand it in terms of epsilon to actually get what h is exactly. Okay, so the only basic difference of introducing this omega squared is these two guys. Go through it systematically and make sure you get the same answers. So it's actually a good exercise to take what I did on the previous slide and just do it with this new equation to make sure you understand what's going on. Okay, h over here, as I said, is h of x and x dot. And because there's an epsilon in front of it, you only have to keep the lowest order terms. So it's basically a function h of x0 and d tau of x0. Okay, and once again, you're going to you solve the order 1 equation to get x0, and then you substitute this thing into h, you substitute x0 into our definition of h, replacing x with x0 and x dot with the fast time derivative. And then you've got to also take this mixed derivative of x0 to actually get what the right-hand side is. Okay, so now let's just write down the general solution of order 1. We're going to write down the general solution. It's simply this a of big T cos of the fast time scale, so omega t, and important, this is where the omega is coming in, right? Okay, because you have the omega entering there, so the frequency is omega. So you have a of big T cos omega t plus b of big T sine omega t. An equivalent way of writing this, you have two unknown constants here, you could also write it as r of big T times cos of omega tau times phi of big T. Okay, so these two things are exactly equivalent. You can get the r and the phi if you have A and B, or if you have r and phi, you can get A and B. Okay, this thing just makes it easier to analyze, and it makes it easier to actually get equations that's going to help us estimate the amplitude of the limit cycle. So remember, you asked in the tutorial, can you guess the amplitude of the limit cycle? What's going to happen here is this method is actually going to give us a way of doing that for weak oscillators, provided we write the base solution in this way. Okay, what I'm also going to do to make things simpler, I'm going to say this is the same as writing r of big T cos of an angle, which I call phi, which is a function of the slow time and the fast time, and that angle is simply, the angle theta is simply equals to omega tau plus phi of big T. Okay, so it's just writing the general base solution in a way that's easier to work with. So now I want to do is, the aim is basically to derive equations for r prime and theta prime in a way that you get rid of the resonant terms. Okay, so it's basically making systematic what we did in the previous example. Okay, and that basically means we want the resonant terms are all the terms that are proportional to cos of omega tau plus phi. In other words, the resonant terms are all the terms that have frequencies that have the same frequency as the natural frequency of this oscillator of x1. Okay, so we want to get rid of terms proportional to cos of omega tau plus phi and sine of omega tau plus phi. And so, and it only is up to order epsilon. So we now have x0, okay, and it's a 2 pi periodic function of theta, where our theta is just the thing I introduced over there. And the interesting insight is the moment you have a periodic function, a 2 pi periodic function of theta, you can find a way of expressing it in terms of a Fourier transform. And you also know that its derivative with respect to tau is also a 2 pi periodic function. And so since h over here is made up of, has got arguments that are 2 pi periodic, it itself will also be 2 pi periodic. And that means we can actually write it as a Fourier series. Okay, so I don't know how many of you have encountered the Fourier series before. Okay, so what that means is we can get an expression for h that you can write as an infinite series of constant times cos of k theta and bk times sine theta, and you can actually calculate what these constants are by taking integrals of h. So a0 is 1 over 2 pi, the integral from 0 to 2 pi of h of theta. So you just take an integral. And ak is just 1 over pi times the integral from 0 to 2 pi of h times cos k of theta. Okay, so given h, which you calculate by putting cos theta x and x0 into our original h function that you're given, you can calculate h, and once you've got it, you can work out these integrals, and then you can write it as the series, at least theoretically. It turns out you don't even have to work out all the integrals, you can, because we only need the lowest ones of them. Okay, so this is how we're now going to write h. And the reason we do that is because it allows us to identify which terms are secular. In other words, which terms, the terms that have the same frequency as this fundamental, the fundamental frequency when we put h in there. Okay, so we have ak. We can also define bk. It's just the integral from 0 to 2 pi h of sine k theta d theta.
Okay. And so the thing now is we want to evaluate the right-hand side. And so the part of the right-hand side that does not contain H, so H is easy. We've simply, because it's pi periodic, we write it like this. Okay, we know we can get AK and BK always. So we have H. The thing that remains is this thing that we want to evaluate. Okay, we know that X0 we've written in the following way. And so if we take the slow time derivative of the fast time derivative of X0, we're simply taking the slow time derivative. Okay, the fast time derivative of X0 is simply dd tau. So that is omega coming out times r of t times sine of omega tau plus phi of t. Okay, so that's the fast time derivative that's already been taken in the bracket. And now we want to take ddt of the big beast and we apply the product rule. Okay, so what we get is it's ddt applied to r. So this is just 2 omega times r prime sine of omega tau plus phi plus 2 omega r times big T derivative of this thing. So we have cos omega tau plus phi multiplied by phi prime. Okay, and we can now simplify it by replacing what this omega tau plus phi is. It's just theta plus the second term, 2 pi r phi prime times cos of theta. Okay, and so what we now want is to identify all the secular terms on this right-hand side. And by secular terms, I basically mean all those things that have a frequency of omega, with a frequency omega. Okay, so the secular terms in this right-hand side, we get by simply writing out the whole of the right-hand side. So here is this first time derivative, so it's this basically this mixed time derivative is over there. And so we can see we have secular terms here because theta is basically omega tau plus phi. So we have a secular term there, we have a secular term there because both of them have the same frequencies as the oscillator over here. And then we have this H, okay? And so the way I'm going to write H, which is just this expansion, is to take the first few terms and separate them out. So when k is equals to 0, I have A0. When k is equals to 1, I have A1 cos theta and B1 sine theta. And then I have the rest of the function. Okay. And the thing is, when we want to identify the secular terms, we're only worried about the things that have the same frequency as the oscillator. So we're only worried by these terms, okay, and to make them vanish, we basically want to set the coefficient of cos, the total coefficient of cos to 0, and the total coefficient of sine to 0. Okay, so the vanishing sine term basically implies that r prime is equals to b1 over 2 omega. Okay, and if we write down the definition of B1 now, we simply have that r prime is equals to 1 over 2 omega times pi times this integral from 0 to 2 pi h of theta times sine of theta d theta. And the coefficient of cos vanishing, we basically have the coefficient of cos over there, so it's this term. So it's r phi prime times 2 omega must be equals to A1. So we get this expression. And we know that A1 by definition is equals to that integral. And so those are our conditions that we have vanishing secular terms. And they are the conditions for us to establish what the amplitude and the phase is of the perturbation solution. And so we call these two equations basically the averaged or the slow time equations. And they actually allow us to estimate where the limit cycle is if you can solve for R from this equation, and a little bit about the phase if you can solve for theta from that, or phi from that equation. Just one comment. It's often, when we write these integrals, it's often useful to use this bracket notation. People use it a lot in quantum mechanics. You get it a lot when you take inner products or when you do image processing. So I just want to give you the definition of it. Those brackets basically mean if it's a function of theta, g is a function of theta, and you're going to take their average. In other words, the integral from 0 to 2 pi of f theta, g theta, d theta, and divide by 2 pi. So it's the angular average of that product. Okay, so we now have these equations. How do they work? Okay, so we've derived them using this two-timing approximation, and then just the extra trick that h is a periodic function because x0 is effectively a periodic function. And now we simply want to see how they work, and we're going to look at the van der Pol equation as an example. So there we have our van der Pol equation, and it has omega equals to 1, and it has this is h now. Okay, and now we have our initial conditions of x0 equals to 1 and x dot equals to 0. We basically want to find and solve the averaged equations, okay, to find an approximate solution to x of t and epsilon. So this is now a non-trivial example, okay. And so we have omega equals to 1, just to put it in the form that we've had, and we have h equals to x squared minus 1 times x dot. Okay. And we're going to substitute x0, which we now know because omega is equals to 1, is just r cos of theta into this expression. Okay, so there we have x0 is just r cos theta, so that's squared minus 1. X dot is minus r sine theta. Okay, and our averaged equations are now r prime is equals to 1 over 2 pi, the integral from 0 to 2 pi, h of theta is sine theta, and which we can write as like so. And the second averaged equation is just r phi prime, the integral from 1 over 2 pi divided by 2 pi of h of theta cos of theta. And so all that's actually required to figure out what r is to actually evaluate this integral. Okay, and you can see that h of theta has functions of theta as well as functions of r, but the integral is only over theta. So if we start evaluating it, right, we're going to have h sine theta is simply this expression. Okay, you multiply out the expression and you actually do the angular integral. Okay, so that's just grouping the terms. It's cos squared theta, sine squared theta, and you can take the r outside, plus r times sine squared theta. Okay, and the integral from 0 to 2 pi of sine squared theta is a half. Okay, this thing you can also write as sine squared of 2 theta, so it's also once again just to work out the integral. Okay, plus r over 2. This thing is also a half, right? And so you get, to evaluate this right-hand side, you have r to the 3 over 2 to the 3 plus r over 2. And so you now have that r prime obeys this equation. And so it's a one-dimensional differential equation, which you can then solve. And that will give you in some sense, the averaged radius evolves. And if it has a fixed point, that's the period of your limit cycle. Oh, that's the size of your limit cycle. Just to practice the R phi prime, which will give you the average frequency in the way. You want to work this thing out as well. So it's a sine theta cos theta times this bracket. Okay, so it's basically r to the cubic, you multiply it out, sine theta cos theta to the 3, plus r times sine theta cos theta. But this thing is just the derivative of cos to the 4, and because it's a periodic function, it's simply 0 if you take the average. And this one is also, there's missing a derivative sign there, but it's a derivative of cos squared d theta. And because you're integrating from this effectively the same spot from 0 to 2 pi, they're 0. Okay? So there's going to be no shift in phase, but this radius is going to obey this equation. So you basically, the interesting thing is that r prime is equals to that, and r phi prime is equals to 0. So those are your averaged equations. If you integrate them, okay, you can integrate this thing just by breaking it up into partial fractions. You can actually get what the slow time and r relationship is. In fact, you can get r in terms of the slow time, okay, by simply doing the integral. And then you take the exponent, okay, and I'm going to actually, give me 2 minutes and I can finish it. Okay, so you've got this relationship of your r implicitly of r in terms of your slow time. You now need your initial conditions that basically says when t is equals to 0, x is equals to 1, okay, and x dot is equals to 0. What you're going to do now is you know that r of 0 is equals to the square root of x0 squared plus x dot of 0 squared. And so that's equals to 1. Okay. And you know that phi of 0 is equals to tan minus 1 of x dot over at 0 over x of 0 minus tau. Okay, and you're going to know that that's equals to 0. So you're going to basically put this back into these assumptions back into this equation, and you're going to have that at times t equals to 0, you're basically going to have that r of 0 is 1. So you're going to get an expression for this integration constant, right? And then you get that c is equals to ln 3, and therefore if you take the exponent of this whole expression, what you're going to get is that e to the t is equals to 3r squared, 2 squared minus r squared. And if you can invert this, you can solve for r because it's just a quadratic expression, and you're going to get that. Okay. So you now have how your amplitude evolves on average in time, and you can write down what your solution is, the approximation, simply by putting in your amplitude r of t times cos of t, and you can actually plot that and compare it to your integrated thing. You'll find it's exceedingly close. Okay, so in some sense you've got an average solution for your van der Pol oscillator, and you can see if epsilon goes to 0, the limit cycle is at r equals to 1, and as epsilon changes, it's sort of the limit cycle changes. It remains at r equals to 1 and it decays to it. Right. That's the end of the story for today. Any questions? Okay. This thing is not hard. It's very mechanical. So you actually have to go through an example to understand it. And you've got a couple that I'll put up. You don't have to hand them in, but please do go through them so that you can get fit and you can actually see what I did. Like, go through the way I've calculated the derivatives, that you know how the structure comes in and how we actually derive these amplitude equations or these averaged equations. Okay. And a lot of physics and mathematics uses this type of thing. Whenever you get complicated equations and you actually want an analytic estimate of your limit cycle, you're going to be doing averaged equations. So thank you very much. Any questions further? Yes. Do you want to go?